Okay, so today we're going to talk about group homology and cohomology. Since this is the last lecture in the series of lectures on homological algebra, I'm going to assume everything that has been done so far. In particular, I assume basic definition and properties of abelian categories, chain complexes, uh, derived functors, delta functors, derived functors, and tor, ext, yeah, etc. So let's just start. So what is a G module? Now, if G is a group, a G module is nothing but an abelian group with an action of G. So it's a group acting on an abelian group, but group G acting on an abelian group, but with the fact that it preserves the structure of A. So G dot A1 plus A2 is G dot A1 plus G dot A2 for all A1, A2, and A, and for all G and G. So this is a G module. Okay, fine. Then we would like to define morphisms between such kind of G modules, right? Natural thing to do. So if you have two G modules A and B, we say a map F from A to B is a G module homomorphism if first of all it's an abelian group homomorphism, and but also it should preserve the structure of the action and also preserve the action of G, right? So F of G dot A in particular is G, so F of G dot A is G dot F of A for all G in G and for all A. Okay, so now we denote such morphisms by the collection of all such morphisms by Hom G A comma B, and you can see that this is actually a category. With this definition of objects and morphism, this actually forms a category which we denote by G mod. Now, the fact that we have a abelian group with an action of G on it is equivalent to defining a homomorphism from G to the automorphisms of A. So here, aut A is the set of all abelian group isomorphisms of A. For every G in G, the map A goes to G dot A is isomorphism of abelian groups. So that's the equivalent definition, another way to think about it. Yet another way to think about it is in terms of modules over the group ring, integral group ring. So if you have a G module, then you have an action of G, but you can extend that action of G linearly to the action of this integral group ring ZG. Like this very obvious way you can do that. You can take any summation AGG, it acts on A just by acting G and acting the G on A and then summing over all AG. So it's a linear extension, and this definition makes A into a left ZG module. Conversely, of course, if you have any ZG module, it's already a G module because it's already an action of G because G is contained in this group ring. So in this way, G modules are nothing but ZG modules, and in fact, this actually gives an isomorphism of categories. The category of G modules is the same as the category of ZG modules. I'm talking about left modules. And this in particular shows that the category of G modules is a abelian category because ZG modules is an abelian category, modules over any ring. Then we can also think about this category of G module as a functor category, right? Because any G module, you can think of it as a functor from this category G, and this is a category with single object and morphisms being the elements of G, to the category of abelian groups, right? And so this also gives isomorphism between the category of G module to the functor category from G to abelian groups. Okay, now let's see some examples of G modules. First, there is a very simple or trivial example, that is, if you have any abelian group A, any abelian group, I can turn into a G module by the trivial action of G. I just define G dot A equal to A for all G, right? This is what we call a trivial G module, and in fact this is a functor. This gives a functor from the category of abelian groups to the category of G modules, right? Another example is that if you take a G representation, so it means that a linear G representation, that means a homomorphism from G to this general linear group, which is nothing but the isomorphisms of V. Okay, so this V is nothing but V is a vector space over K, over a field K. This is also a G module, and the reason is that because this collection of all invertible linear transformations GLV is automatically contained in the collection of all homomorphisms, isomorphisms of V considered as an abelian group, if you just forget the structure of the scalar multiplication. So this is already a G module. Then another interesting example comes from Galois theory. If you have a Galois extension L over K, and suppose G is the Galois group, then this Galois group naturally has an action on the abelian group, additive abelian group of the field L, and also the multiplicative abelian group L star. Why? Because the Galois group is contained in the automorphisms of L, in the abelian group automorphisms of L, because any automorphism of L is already an automorphism of abelian group. Also, it restricts to an automorphism of the multiplicative abelian group. So in both cases, this defines a structure of G module on L and L star. So we'll talk about this particular G module later. Then let's look at this functor, trivial module functor. The point is that this trivial module functor from the category of G abelian groups to G module is actually an exact functor. Now why is that? Because if you think about the category of G modules as the functor category G to AB, this functor is nothing but the constant diagram functor from abelian groups to G of abelian, G comma AB. That is, if you recall, the constant diagram functor was used to define limits and co-limits from the category C to the category, the functor category, diagram category, J to C. Now, since the category of abelian groups has limits and in fact it has all small limits and co-limits, this functor has both left and right adjoints, because the left adjoint of this functor is the co-limit and the right adjoint is a limit. So because abelian groups has all these things, so this has left and right adjoints. So this tells us, and G is already a small category, so this tells us that this functor, so this tells us there's a functor, the trivial module functor also has both left and right adjoints, and which implies that it preserves all small limits and co-limits, and hence it must be exact. Yeah. So that's one way, nice way to see that it is exact functor. Now we know it should have right and left adjoints, so if you try to figure out what the right and left adjoints are explicitly just using the Hom bijection between the Hom sets, it's easy to figure out what the right adjoints and left adjoints should look like. So the right adjoint is this functor which takes a G module and just gives you the G invariants, like all elements in a subgroup which are preserved by or which are fixed by any G element, fixed by any action of any G in G. So G dot A is equal to A. So that is G invariant. So this is a subgroup of A. This is the right adjoint. Similarly, the left adjoint is it takes a G module and you quotient it by this submodule generated by the set G dot A minus A for G in G and A in A. So look at this set and just take the submodule generated by that, and the quotient is this so-called coinvariants, G coinvariants of A, and this is the left adjoint. So it's very easy to check that this should be the left and right adjoints just by explicitly looking at the Hom bijections. Now, okay, so these functors are there. Then we can also describe these functors in a familiar way, in terms of familiar functors. So this is this lemma that if you consider Z as a trivial G module, then this coinvariance functor is naturally isomorphic to this tensor over Z tensor over ZG, and the invariance functor is isomorphic to this Hom functor. Now here Z is considered as a right ZG module by the trivial action and a left Z module. So it's a ZZG bimodule, and in here the opposite is happening. Here it is considered as a left ZG module. So so why is that? So if you consider Z as a ZZG bimodule, then this functor tensor product we already know has a left adjoint of Hom, right? The tensor Hom adjunction. If you use a tensor Hom adjunction, we know that this functor Z tensor over ZG is left adjoint to this functor Hom Z dash. Now what is this functor? Now this, remember, is a functor from G mod to ab, and it given any abelian group, sorry, this is a functor from abelian groups to G mod, and given any abelian group A, Hom Z ZA is just A, right? It's isomorphic to A. But if you view Z as a if you view Z as a right ZG module, then this Hom set also has a structure of a left ZG module, and this structure, when you put on A, this becomes a trivial module. So this tells you that this functor Hom Z comma Z dash is isomorphic to the trivial module functor, and since this functor has left adjoint given by this tensor product and adjoints are unique up to a natural isomorphism, this suggests that this the coinvariance functor is naturally isomorphic to this tensor product. Now for the other functor, if I take any G module, then notice that the coinvariance AG is isomorphic to this Hom Z Z AG. That's like for any abelian group that is true. But now using the fact that this functor invariance G invariance is a right adjoint to the trivial module functor, you have this isomorphism between the Hom sets. This is isomorphic to the Hom over ZG modules of Z comma A. Here you consider uh, Z as a trivial G module. So this tells you that this functor is isomorphic to Hom G Z comma dash. This isomorphism. This is isomorphic to this. So this completes the proof. Now, so now we have these functors, the coinvariance and invariance functor. They are they are left and right adjoint respectively, and also your category Gmod has both enough projectives and enough injectives, because it is isomorphic to a module category, and module category already has enough projectives and enough injectives. So we can talk about the left and right derived functors. Yeah. So these are precisely the so-called homology and cohomologies. So we define them formally. Given any left G module A, we define the homology groups. We define the homology groups of G with coefficients in A as this H sub n G A is defined to be the nth left derived functor of this coinvariance functor at A. Yeah, so at this object A. Similarly, the cohomology groups are defined to be, with coefficients in A, are defined to be the right derived functors of this invariance functor at A. Now, but we also know this alternate description of these functors in terms of tensor products and Homs, and we know that tensor products has left derived functors given by the Tor functors. So this tensor product has left derived functors given by Tor ZG Z comma dash, and this Hom has left right derived functors given by X and ZG Z comma dash. And since we know that these are universal delta functors, they must be unique for a given functor or two functors naturally isomorphic. Their left right functors are unique up to isomorphism. So therefore they suggest that the homology functor is nothing but this Tor functor, and the cohomology is this Ext functor. So once we have the description in terms of Tor and Ext, things become better, right? Because now to compute these homologies and cohomologies, we can just start by taking a projective resolution of Z. For Tor, we will have to do that, take a projective resolution of Z and apply the functor tensored with A, and tensor the projective resolution P, suppose, with A, and compute the nth homology. For the Ext, we can start with injective resolution, but also now we can take projective resolution because of the fact that X is balanced. I can take a projective resolution of Z, and then I can apply the functor Hom G dash comma A. It's a contravariant functor, so we'll turn the chain complex into a co-chain complex and then apply the nth cohomology to compute this. So okay, so let's try to see some examples of this computation. So if you have a trivial G module, then the zeroth homology is and the cohomologies are like just given by this invariance and coinvariance. If you have a trivial module, then definitely there is no coinvariance and invariance. I mean, the coinvariance is just A and the invariance is also A, like by the definition. So this is there. Then if G is trivial, then these functors are, first of all, the group ring is nothing but the category of abelian. The group ring is just abelian groups. The category of G modules is nothing but the category of abelian groups. Yeah, Z modules. So this tells you that, and also these functors are the identity functors, right? So since these functors are exact, the left derived and right derived functors of an exact functor are zero. Higher left derived after n, for n bigger than zero. Yeah, so the higher cohomologies and homologies are all zero. Then if G is a isomorphic to Z, if it's an infinite cyclic group, let's say generated by T, then you see that the group ring is nothing but the sequence of all, I mean, finite sum of polynomials with integral coefficients. Polynomials in what? Polynomials in powers of T, but all powers of T, integral powers of T. So it is positive powers of T and T inverse. So essentially it's a ring of integral log of polynomials. So polynomials in T and 1 by T. So to compute homology and cohomologies, we would like to get a projective resolution. So let's try to do that. So first of all, I take this Z and I have this map from ZG to Z. What is this map? This epsilon map just takes any polynomial and just puts T equal to 1, substitute T equal to 1. Essentially, you are substituting any group element G, you are substituting 1. So this, you get this map epsilon. Notice it's a surjective map. Also, Now the question is, what is the kernel of this map? Yeah. Now, so the kernel will be all polynomials p such that when I put t equal to 1, I get 0. Now, if you have any polynomial p, log polynomial, I can always multiply by a higher power of t to the n. So that t to the power n times p is nothing but a integral polynomial with integers. We can clear the denominators. And then, since this integral polynomial vanishes at t equal to 1, by the division algorithm, it is a multiple of t minus 1. So the polynomial p is a multiple of t minus 1 in this ring. So this suggests that the kernel is precisely the set of all polynomials which are multiples of t minus 1. So essentially, if I take this zg and take this multiplication by t minus 1, the image of this map is precisely the kernel of this map. So this sequence is exact at this point. Also, this map is injective, the multiplication by t minus 1, because this is an integral domain. Notice it's a commutative ring and also an integral domain. So this is injective. So this is the projected resolution. So with this, you can immediately see that the higher homology and cohomology, that is for n bigger than 1, they are all 0 because there are no terms beyond that in the projected resolution. And then to compute these first cohomologies and homologies, you apply the functor tensor with A, and then you apply this Hom functor. When you apply the tensor product, you get this chain complex. Obviously, you are tensoring Zg with A over Zg, so you only get A. So you just get this chain complex with this multiplication t minus 1, and for this applying a Hom functor to get this cochain complex. They look same, but this is the this is a chain complex. So this is the 0th degree, this is the first degree. Here this is the 0th degree, this is the first degree. Because of that, the homology and cohomologies are interchanged. The first cohomology is the same as the 0th homology, and the first homology is the same as 0th cohomology. And we know what 0 and 0th homology and cohomologies are. They are the invariants and co-invariants. Okay, so right. So next we define what we call this augmentation map. Recall this map earlier we said this epsilon from zg to z, which just sends every group element to 1. Now, so this is this map. So we just define this map from z to z, sending every group element to 1, extended linearly. So it sends this summation g and g, ag g2, summation g and g, ag. Notice this map is just z linear, but also you can make it a ring. Actually, it's a ring homomorphism. It's a ring homomorphism, and it's also a map of zg modules with z being the trivial g module. So this map is what we call the augmentation map. And the kernel of this map is what we call the augmentation ideal. It's a two-sided ideal of this group ring. We know it by J sub G. Then, if you recall this ZG, it's an integral group ring. This is a free abelian group with bases given by the group elements G. But also, you can also say that the set consisting of the identity element and the elements G minus 1, where G is not identity, this is also a basis, clearly. Which means that since every element here G minus 1 is already in the augmentation ideal, because when you put G equal to 1, it just goes to 0 under this augmentation map. So it tells you that this augmentation ideal is actually a free abelian group generated by this set of G minus 1, where G is not identity. This is also free abelian. Okay, so with this, let's try to compute some homology groups, zeroth homology in particular. So zeroth homology of G with coefficients and A is just this co-invariance, which we have shown already, this isomorphic to Z tensored with A. Notice that this map is surjective. This augmentation map is surjective. So therefore, Z is isomorphic to ZG modulo the kernel, which is this augmentation ideal. So you can write this Z as ZG mod JG tensored with A, which by the property of tensor product is A mod JGA. So now if you compute the homology with Z equal to Z, then this is just a Z mod JGZ, but the action of JG on Z is trivial, right? Because G minus 1 acting on any integer, because it's like G dot A minus A, or G dot A is just A because of the trivial action. So this is just 0. So this is Z. Similarly, if you want to, next example is when you take A equal to ZG itself as a ZG module. ZG, you can make A equal to ZG. Here, you'll get again ZG modulo using this formula, ZG modulo JG, but which we know is isomorphic to Z. So that's this. And then if you calculate this zeroth homology of G with coefficient in this JG, then this is again JG mod JG square using this formula. Then if you calculate, okay, so then for this particular case, a equal to zg, we can calculate the homology. We already calculated the zeroth homology, right, which is z. The higher homologies, they are just zero. Why? Because this is just nothing but the tor, and zg is a projective zg module, hence they are all zero. So what about cohomology? Now here for the cohomology, things get interesting. It's not necessary that they may be zero, but it turns out that for finite groups, if G is finite, then the higher cohomologies, they vanish. And this is something which we'll see later. Why is that the case? But for infinite groups, it's not necessarily true. For example, we have seen this case that if G is the infinite cyclic group, then we've seen that the first cohomology for any A module, for any G module A, was nothing but the zeroth homology. So in this case, the first cohomology of G in ZG will be the zeroth homology, but the zeroth homology is already equal to or isomorphic to Z. So this is nothing but Z, which is not zero. Okay, so this is something true for finite but not for infinite. What about the zeroth cohomology? This is a higher cohomology. What about the zeroth cohomology? Now notice that if you take zeroth homology is nothing but the G invariants, right? I have to calculate the G invariants. Now, so already you can see that what if G is finite, then if you look at this linear combination summation G in G, G, this is an element which is preserved by every element of which is an invariant. Like if you multiply any G prime by this element summation G in G, then over G, then this is just the same thing. That motivates the definition of this norm element. For a finite group, we define this to be the sum of all the group elements in this group ring. Then we know that for any G prime, if you multiply G prime by n, we get this thing, but this runs over the same group element, so this is just n, which is also you can write in this way because it's the same. So it tells you that G prime n is n, which is ng prime, which gives you that n is actually in a G invariant, but also it is in the center of this ring. And so that is fine, but so n is there, and all integral multiples of n will be there, yeah, in this invariant for the G invariants. But in fact, these are the only G invariants. That's easy to see. If you have a summation AGG, which when you take any G prime is the same, then you have to all these coefficients must be the same. So they must be. So for finite group, the zeroth homology, the cohomology, which is this invariance, is nothing but Zn, this subgroup generated by n, which is isomorphic to Z. Now for an infinite group, when you take any summation, any finite sum of these linear sum with coefficients in Z, and then if it is a G invariant, the thing is that you can always, since G is infinite, you can always choose a element G, so that when you multiply it by any of these finite GIs, then it will land outside this finite set. Because G is infinite, you can always find such a G. So that suggests that when you take that G and multiply, then you'll get an entirely different set of basis elements here. So that means that these coefficients must be 0. For that to be 0, all these coefficients must be 0. I mean, this is equal to the original one, but so this is so that means that there is no non-trivial G invariant element here. So that means the zeroth cohomology in this case is 0. Now let's see some relationship between this augmentation ideal and this norm element, obviously for finite groups, which will be helpful later. So note that we observe that this is obviously isomorphic. This zeroth homology, this is a Z, the subgroup generated by n. This is obviously isomorphic to Z as abelian groups, but also it is isomorphic to Z as ZG modules. This map which sends just n to 1. Now let's try to see if we take any element in the group ring. Let's say what happens if I multiply it by n. Okay, so if I multiply this by n, then n will go inside and I get this ag ng summation over g in g. Now ng is nothing but n, right? And then I can take out this n outside and I have this summation g in g ag, which is an integer, so this belongs to z times n. So this suggests that this map between a map of g modules, zg modules, from zg to z multiplication by n, this surjects onto this zn, z dot n. This surjects onto this subgroup. So now we know that if you compose this map with the isomorphism to z, that is which sends n to 1, you can easily see that you get the augmentation map, because any arbitrary element summation agg here goes to this element in z dot n, but then Under the isomorphism with Z, you just take n to 1, so this gets summation G in G AG. So that is precisely the augmentation map epsilon, whose kernel is the augmentation ideal. Therefore, the kernel of this multiplication map itself is also the augmentation ideal GG. So this observation will be helpful later on. Okay. Now, what can we do now? Let's try to compute some homology groups. Okay. Um, so there's this important lemma first that comes up. That is the JG mod JG square is isomorphic to G mod the commutator subgroup of G, which is the abelianization of G. As abelian groups, they're isomorphic. That's easy to see actually. First of all, you define a map from let's say G to this JG mod JG square, which just sends an element G here. Remember, these JGs are generated as Z modules by G minus 1. So just send G to G minus 1 bar. So this is an element here, that's fine. But you have to check it's a group homomorphism. But since this is an abelian group, this is in general arbitrary group, so the commutator subgroup of this will go to 0 because it's abelian and it's a homomorphism. So this induces a map from the abelianization of G to this JG mod JG square. Similarly, you can define a map in the opposite direction from JG to this abelianization of G, which sends a basis element, let's say G minus 1 to G bar. And again, you can check it's a group homomorphism, which induces a map from JG mod JG square to the abelianization. And clearly, these maps are inverses of each other, which shows that these are isomorphic. Now, this observation helps to prove that the first homology of G with coefficient is Z is nothing but the abelianization of G for any group. So here, you consider this consider this short exact sequence. I mean, this because the kernel ZJG is the kernel. This is the augmentation map, and JG is the kernel of that. So this is the short exact sequence, and corresponding to the short exact sequence, I have a long exact sequence of homologies. Essentially, this is a long exact sequence of TOR, like this. Now here, you observe in this long exact sequence that this is 0 because ZG is projective, so this is like 0. And notice that this, remember, is isomorphic to Z. In the previous slides, we've seen that. And this is also Z is trivial Z G module, so this is also isomorphic to Z. And in fact, this is an isomorphism. This map is an isomorphism between these two groups. So since this is 0, this and this is isomorphic, this and this is a long exact sequence, this also this and this are also isomorphic. So once these are isomorphic, so H1 of GZ is isomorphic to H0 of J and JG, but this we already seen is JG mod JG square, which we now see by the previous lemma is the abelianization of G. Okay, so that is fine. So this answers the question about the first homology with coefficient in Z. Now you may ask, what about other G modules? And it turns out if you take a trivial G module, then it's like done. There's nothing. I mean, this Z will already answer those questions. So this is given by this theorem. If you have any trivial G module, then you have this split exact sequence. Like the nth homology of G with coefficients in A is related to the, in fact, the direct sum of these two groups, abelian groups. This is the nth homology of G in Z and the nth homology, n minus 1 homology, and this TOR correction factor is there. So, how do we do this? So, if you look at any free resolution of Z as ZG modules, then note that to compute this thing, what you need to do, you need to figure out, take this tensor product Pn tensor with Zg over tensor Zg with A, right? Any Pn in this complex. But note that this is A is isomorphic to Z tensor A, right? Because A is a trivial G module, so you can write this A is isomorphic to Z tensor Z over A, Z tensor Z A, and hence this becomes this, and now by the property of tensor product, this is isomorphic to this. So now note that this complex, I mean this Pn is a free Zg module, hence Pn tensored with Z over Zg is a free Z module, free abelian group. So once you have a free abelian group, you have a complex of free abelian groups, which is P tensored Z. This P tensored Z is the complex of free abelian groups, and then I'm tensoring this with A. Then I will get this thing. So because this is free abelian group, I can apply the universal coefficient theorem for homology to conclude that the homology of this complex is related to this two separate homology. I mean, you have a split exact sequence, and the homology of this complex tensored with A over Z is nothing but this group homology, and the homology of this itself is the group homology with Z. So that gives this theorem. In a similar way, you can establish a relationship for a cohomology using the universal coefficient theorem for cohomology. Okay, now let's compute some homologies and cohomologies for groups where we can compute, for instance, cyclic and free groups. Now for cyclic groups, suppose G is a cyclic group generated by sigma. It's finite, infinite we have already done, so it's like isomorphic to Z mod mz, and then you have to get hold of a projective resolution of Z. Now first, any finite group, you already have this short exact sequence. This, remember, comes from our previous observation, and this map multiplication by n map has a kernel Zg, and this is surjective. So this is a short exact sequence that is already there. Now what is the norm element here? That is this summation 1 plus sigma up to sigma to the n minus 1, which means that sigma minus 1 annihilates n. So okay, now if you look at this map from Zg, if you take any Zg multiplication by sigma minus 1 on Zg, right, what happens? Notice that this Zg is Jg is generated by sigma to the j minus 1, right? When this is like the g minus 1, and so that means that all of these are multiples of sigma minus 1, and sigma minus 1 is already in the augmentation ideal. So therefore this suggests that the augmentation ideal is nothing but sigma minus 1 Zg. So this suggests that this map from Zg to sigma minus Jg multiplication by sigma minus 1, this is surjective. Now what is the kernel of this map, right? So if A is in the kernel, then sigma minus 1 A is 0, which means that sigma dot A is equal to A, which means that sigma to the power j dot A equal to A for any j, right? So that means A is a G invariant, which means A is in Z dot n. So that's the kernel. Okay, so that means we have the short exact sequence. Notice these are very similar, they are interchanged. Because of this, I get a very nice resolution of Z. I just take this augmentation map in the first place, and here I take this notice that the kernel is of this map is the augmentation ideal, but I need something, therefore I need something to surject onto that, and I take this Zg, which is projective multiplication of sigma minus 1, which surjects onto Jg. But this map, remember, now it has a kernel Zn, Z dot n, so this has a kernel Z dot n, therefore I need something which surjects onto that, which is obviously the multiplication by n map, and so on and so forth. This continues. So this have this periodic resolution, right? And then to compute the homology and cohomology, just apply the functors, tensor products, and hom, and then you can get. And in fact, in this case, it's the odd homology groups are equal to the even cohomology groups, and the odd cohomology groups are equal to the even homology groups. Like it's there. What about free groups? Now, free groups also something we can do. Now, suppose J is a free group on a set X, and then it turns out that the augmentation ideal is also a free Zg module, which is generated by this set X minus 1. So why? Let's try to see that. So if you have, so notice that Jg is already free abelian generated by this set G minus 1 for G not equal to the identity element. Now, if I take any G which is not identity, then it's a free group generated by X, so it's a word. Word means a bunch of symbols of X and X inverses, a finite linear product in some sense. I write them in this way, and suppose that that word ends in some symbol X in X, right? That means G is like G prime times X for some G prime in G. Notice that I'm taking this as a reduced word. I mean, we cancel all X inverse if there are any already in G, right? Then so this ends in X, let's say. Then what about G minus 1 is this G prime X minus 1, but notice that this is equal to G prime times X minus 1 plus G prime minus 1. So this identity holds. Similarly, for G, if it ends in X inverse, then the corresponding identity holds here. It's like G double prime X inverse, then this identity holds. G minus 1 is equal to this thing. So what does this tell you? This tells you that I can take any G minus 1 and I can rewrite it in terms of this set. Set is this G X minus 1, G in G, X in X. In terms of this set, just a linear combination of these. How? I take G minus 1, already I can write it as g prime times x minus 1 plus g prime minus 1. But this g prime, remember, is again of the same form as g minus 1, and g prime is having one length of g prime is one shorter than g. By induction on the length of g, word length, I can conclude that any g minus 1 I can write in terms of this set. Also, if I take any element of this set, by again from these formulas, I get that I can write them in terms of the original basis g minus 1. This tells me that by this interchangeability that this set is also a basis of JG as abelian group, Z basis. So since it's a Z basis, I can take the G out essentially, and now this x minus 1 only itself, this becomes a ZG basis of JG. So that's the point. So that is why I get a free ZG module. Now with that, things are very now easy, because since now JG is free, this short exact sequence itself becomes a projected resolution because this is now a free module. So this automatically tells you that the higher homology and cohomology, which means for n bigger than 1, they are all 0. The 0 and 1 you can compute depending on what A is. It's not hard. Okay.